proposition that this G with the convolution is a monoid. It's even convex monoid, we'll talk about this, but at least for now it's a monoid where the unit of this monoid, or what we call the identity, it's called the identity. Then is delta of E, where E is identity is E is the E the in G. Okay. So this delta of A, you remember this distribution delta of A, maybe let me remind you what I mean by this. Delta, when we say delta A, like we mean like that it's the distribution that for on any B, it's equal to 1 only if B equal to A, and it's 0 otherwise. We should not. Okay. Okay. So let me give some examples that it's important for us. Let's take the distribution on this Klein group, Z2 cross Z cube. Klein group, you know, Klein group with okay, obvious like here the sum is the multiplication here in this group, the sum. There is only 4 edges, but this is okay, this is finite, but this is infinite. The distribution on this is infinite. This is finite, only 4. There is 4 elements here, but this is infinite. So we will take distribution. So let's use this notation. I will use this notation. I will write it as the boxes, or as we can say as matrices, like, or as the boxes. When I mean like here, I put, yeah, okay, let me write this notation on side. Like when I have a distribution on this, P and Q, so P, I can write it, P, I can write it like this, like P of 0, 0, what is, because here there is 0, 0, so P of 0, 0, I will put here, P of 0, 1, I will put here, because what is distribution on this? Distribution on this is, it's 4 numbers, that the sum of them is 1, right? The sum of this is 1. What is like the distribution on 0, 0? What is the distribution 0, 1, and 0? So I can put them on the matrix like this. So let's choose 2 like this. Okay. Like this is P, and this is Q. This, instead of writing, like, you remember from this what I mean, because this, instead of writing that P of 0, 0 is quarter, and P of 0, 1 it's half, and things like this, instead of this I will write it as a matrix, and you remember the places, yeah, where 0, 0, where is 1, 1. So let's see what is the convolution give me if I doing convolution for this. It will give me new distribution here. So let's say what it's on 0, 0, for example, what is the result. So back to the definition, we should take all the sum that give me, which sums that give me 0, 0. So we know that the sums that give me 0, 0, it's 0, 0, and 1, 0, 1, 0, right? 0, 0. It's like if I take P on 0, 0, product Q 0, 0, because the sum of this will be 0, 0. But also if we take this 0, 1 and 0, 1, this will give me same. And if we take 1, 0, 1, 0, 1, 1, 1, right? Yeah. And let's say what it's equal to this one. It's quarter, and this is half, right? We take this product. This one is 0, 1, it's half, and here it's 1 over 8. And so on. This is 1, this is 0, this is okay. At the end, I already calculated it. So at the end, we will get 7 over 32. So it's not enough. Okay, we need also to calculate this. We need to do. I will not doing all the calculation, but let just the beginning of 0, 1. Which ones give me 0, 1? It's also there is 4 pairs, right? It's 0, 0 is 0, 1, right? The sum of them will be 0, 1. But there is others like 0, 1 with 0, 0, of course. And there is 1, 0 with 1, 1, right? So 1, 1. It's give me, because the sum of this is 0, 1. So it will give me 0, 1. And of course, 1, 1 with 1, 0. And if one calculate it, it will turn off that it's this is a number. And at the end, if one, of course, we need to calculate also this 1, 0, and what is the result for 1, 1, solution of 1, 1. If one calculates this will be 1, 0, 9 over 32, and this one will be 5 over 32. At the end of the day, so we will get, we can write here that the new distribution, we can write it as matrix as with, okay, before, like it's this one. Okay, so it's some calculation, like it's, so this is how we calculate it. And you can see that the sum of this is 1, right? Like 7, 18, 8, here we have, no, yeah, so sum is 1. Okay. Sum of this, of course, it's well defined, like, so of course it's well defined. So how we can really see that it's well defined, I will show you, like without checking. One can check by the formula, but yeah, I will give another example, and we come back to the where this formula coming from, and then one can realize directly why really it's well defined. Okay, but let me maybe give another example. So this is example 1. Okay, I will give another important example. Yeah. What now if we the same, I want to in the same, like if we take now general distribution P0, 0, P. And we take this, we take the product of this with this distribution. This is called the uniform distribution, like all the same. What going to happen? So of course it will be this quarter, because if we think a little bit like what we should do, like we all the time take by the sum, so we will take like something like this with this, and this with this, and all sometimes with some permutation, like this with this and this with, but at the end of the day, like every way, every way we will get the quarter p 0, 0 plus quarter p 0, 1 plus quarter, right? And the same here, something, but okay, it's only the difference by the order, but it doesn't matter, it's only sum. So at the end, we will get what is this? This is the sum of this is 1, right? P0, 0, P, the sum of this is 1. So this will be quarter. So this will give me, yeah. So this is general in such monoids, the distribution monoids. This is general, so we can write it like in general for you can see now, Jihan, you can see now, it's okay, or still?
Yeah, I can see. I switched to the
You see,
my
oh,
tablet.
very
My
good.
computer doesn't work for some reason.
Very good. I actually started to teach in this one because it's a new version of this Zoom, the whiteboard. So if
Oh,
someone
okay.
has a problem, because some student told me there is a problem when I was like, you can stay up and you, by the way, you can move by yourself. Like every one of you can move this up or down by yourself.
Oh, okay.
Yeah, it's like this. It's because it's for teaching. They move it like this, like student can back.
Oh, I
Yeah,
see.
see
Okay,
what?
so maybe that version doesn't maybe my
Yeah,
laptop
it's
not
version.
supporting that.
It's only 1 week before, so it took me time to, yeah.
Okay. Well, I'm okay for now. I think I'll fix it.
Yeah. Okay. Okay. In general, for what I want to say, like for a finite group G, for finite group G, we can define the uniform distribution U to be U of every A and G, it will be one over how much elements, the order of a G, how much element in G. Okay, this is the uniform distribution, and it has a following property, like this distribution here for every A, I mean for every A in G. Okay, okay, this distribution has this property, what we explained by the example. So this property one can prove in general, like it's not in general. So this distribution has the following property. It's if we take U and do the convolution with any distribution, it's will be U, or from this side or this side, it doesn't matter. Because maybe I didn't say this, but this it's depend on G. Like if G not commutative, not abelian, so dg not abelian. Okay, it's abelian if and only if G is abelian. So it's the convolution not always abelian. Anyway, this will give me the uniform distribution for every P on the distribution, in the distribution on G. Okay, now I wanted actually, yeah, exactly what I promised you to do, like to see where it's come from, this convolution product that we did before. So in fact, the convolution product is the following composition. the way, we did already this, but maybe I remind you because we did this for categories. This is the same here, like it's a special case of category, group special case of category, or like where we have only one object. But if we take this and we take, you remember this M, we said that we have this M from there is alarm. I have to stop. There is alarm because of the war. I have to stop for 2 minutes. I will stop. Okay.
Oh, so we have a break for 2 minutes? So I couldn't catch that. Okay, okay. Yeah, I thought I misheard. I thought I misheard. Okay. Well, maybe I can. Maybe not.
I'm still here actually. But
Oh, okay.
because family came here, it's I am in the room that this safety room, like you know, there is one. Yeah, but yeah, but it's okay. Yeah, and because my son is noising a little bit, but it's okay. Yeah, in 1 minute. In 1 minute, we're waiting until the alarm is gone, but we have to wait 2 minutes or something.
Oh, okay. Okay, we don't hear anything. So yeah. Okay. So let's wait for a minute.
Yeah. Okay. Okay. Let me continue. So we have. You remember this M, the multiplication? What we say, Ali? It's multiplication, and then we apply D of the on. This is the sum on G itself. Yeah, because G have this sum on the side itself. So if we compose this, it's exactly the composition. It's give me the convolution. This convolution. Okay. This will give me this convolution, and because of the property, actually, the naturality of M and no, not the naturality. Which one? It's give me that it's distribution. I think because this actually we know that here if we have two distribution, so this will be distribution, and then this will be distribution. So it's well defined. So far we only prove that this is really distribution. Okay. So that this is the reason why we got there distribution. You see, like here we get distribution by convolution, but it's always because it's really well defined. It's in fact this composition. Okay. Now let us. It's a little bit noisy, or it's okay. It's okay.
I think it's okay. Just very, very tiny bit of background noise. I think it's okay. Yeah.
Yeah, they should waiting for 5 minutes because sometimes after the alarm, something going. Yeah.
Yeah. No worries. Yeah, it's not really disturbing. Yeah.
Yeah.
No.
Okay. So now let me. We actually. So 1 minute. Actually, we're not moving now. Even I want to say something else about. We stay only on the distribution on group. Like how about the convolution? We're not going now to the simplicial distribution. But let me give you some important subgroup of this, and then we can move to the simplicial distribution. So here it's some important subgroups. Sorry. Important subgroups. Yeah. So actually, G, we have this. First of all, it's good to know that we have. We know that we have this delta, right? Delta G from G to distribution on G. But actually, this is a homomorphism. Okay, this will be a homomorphism. So write it. In fact, delta G is a homomorphism of monoid, of course, of monoid, because okay, every group is monoid. So this is a homomorphism of monoid. So we can get the image of this image of delta G give us deterministic, we can say distribution, right? Give us deterministic distributions. Like not simplicial distribution, distribution, like we mean, like if we back to what we have before, like the case when G is Z2, Z2, and we take this like the object 1, 0, so it's will going by lambda of this 1, 0 to this distribution. So as a matrix, as we saw, as a matrix, we can write it like this. Here is 1 and the rest of 0. So it's 1, there is one place 1 and the rest is 0. It's exactly, this is called deterministic distribution. We will have also, we have a version of, simplicial version of this, of course. And then actually also this says that G, because this is homomorphism, but the G is a group, so it turns out that G act on this, right? Okay. G, by this we get, because this is homomorphism, G act, the group G act on the distribution. How it's look like the action? The action, it's like by taking like sound from G by this A. And if I take distribution P, so the action will be by product this distribution, the delta distribution with P, do the convolution product. This is okay. So we have this action. It's important for later. So this actually is the action of the image of this, like the image of G inside here. So inside this we have the deterministic distribution, which is it's form a group. Okay, it's form a group inside this, not only not only monoid. So this is first example, or in general. So the second example, if important subgroup, it's in the case when G is Zm cross Zm. In general, like general M here, we can define, we define S inside the distribution of Zm cross M to be S AB. Here I mean AB in Z2 cross 2. Zm and M, it's will be, okay. So it will be 1 over M if B equal to A plus 1 and 0 otherwise. Okay. So this distribution, how it look like as a, maybe it's good to write it as a matrix. Also here we can write as a matrix when we are, because, but this will be a matrix like this, like here we put the, as we did before, but here we put the place of 0, the distribution on 0, 0, here the distribution on 0, 1, and here's the distribution. Okay, this is the same as this. Sometimes I'm writing like this. Sometimes I'm writing like this. Sorry, maybe that can confuse someone, but it's the same. Okay, here 0, m minus 1. And here 1, 0. So we can write it as a matrix, okay? Like this. So what's that matrix here we have? So we can write it like this. Like it's 0 here, everywhere, and 1 over m up to the. So of course here we have also another one. And the rest is 0. Okay, the rest is 0. So this is what we have, this distribution. Why it's important? Because it's form what is called cyclic cyclic group. Okay, you see. So actually we can define if we do this like S with S, let's say G times. Let's define it to be Sj. And in fact, Sj will be like this, 1 over for AB, sorry, for AB. This will be 1 over M if B is equal to A plus G, and it's 0 otherwise. So this form a group. Like if we take S, we can also define S0 as 0. S0 is the identity, like it will be the, because if we do this m times, what if we do this m times, what will happen? Like here I mean modulo m, of course. Here I mean modulo m, like in Zm. We do this in Zm, okay? So S0, it will be, or Sm, it will be the identity, like I matrix, like this one. It's defined, it's like this. And the rest is 0, yeah? So this form a group. Yes. Mhm. Okay, this form, this is cyclic group. So this important group, we will talk about this later. I can call it the average group. It's called the average group. Was taken by some average, like one thing I forget to say when we, this is exactly what I wanted to say here. Like in fact, dg, or let's write it before we moving to simplicial distribution, that dg is a convex monoid. Convex monoid. So what it's mean? Let me remind you what it's mean. A convex monoid. A convex monoid, it's a monoid, first of all, like we have this product and there is unit, but it's also convex set. Plus, like it's mean like this is convex set plus monoid plus the property that makes them like act good together. Like if we have t between 0 and 1, and p and q, and let's say another one p prime inside j. then T, if we take the convex combination between this, and then we do multiplication with P prime, it will be the same as to do, first of all, the convolution with this and with this, and then to do T and 1 minus 3, and then to do the convex combination. Okay, this will be equal from the, and okay, maybe this is 1 and 2. From the other side, it will be the same. Okay, will not even write it, but it means that from the other side, it has the same property. Okay, this means that the monoid structure and the convex structure act good together. So I think that is for this multiplication, but actually this is exactly the convolution. It's that defined by this convolution. We define the multiplication, the product between simplicial distribution. Okay, so now we move to simplicial distribution. So we can think about what is simplicial distribution actually. In fact, like one can think about simplicial distribution as a distribution, some distributions that like parameterized by this x, by the measurement space, right? Like it's like this, like let's say we something like now of course we want to take this to be like, let's take what we had before, delta of z, m or z2, anyway. Okay. We take this, then we can define a product here. Why? Because let me remind you what is this delta of z2. Let me remind you what this is. This is the simplicial set that in the 0 degree is zm, here in 1 degree zm, and so on. And we have, of course, two faces map here, which is by deleting. We got by deleting, and one degeneracy map by copy, by like I get like what I can be this like A going to A, and here we have two, like A going to AB. Sorry, here can going to this, or can going to this. This is S0 when we apply, and when we apply S1, it's going to this. Okay, this is the degeneracy map. It looks like, okay, by copy in the places. And okay, so we have here also, one can imagine how it's continue. So everywhere we have a group, like, right? Everywhere we have a group, and in fact, it's this is the faces map and degeneracy are simplicial. Sorry, it's homomorphisms of groups. Okay, this is a group. Groups are groups, but it's more even, like this is homomorphism of groups. Okay, let's write this. The face and degeneracy maps are homomorphisms of groups. Okay, so that's the thing. We need not only to be group everywhere, like distribution group, also we need this to be the structure map to be structure visual map to be homomorphism of a group. Then we can define the product here on here. We define the product in simplicial distributions x on this by how we define it by taking, like, if I have two like this, P and Q, if we have we now use small. We usually use small for simplicial distribution. By this, like, then we will get a new one, PQ. How it's defined? It's defined by convolution. Like if we take on some for some x, like x here. So like let's say that x is in xn, then px will be in delta z m plus 1, right? The n here, because in 0 we're going to zm, for 1 we're going to zm cross zm distribution here. So it's will going to distribution here, and qx the same. So we take the convolution between them. Okay, so this will be exactly the convolution between, as we defined before. So it's defined by the convolution. But why it's work? Like what it's give us simplicial things. So this is actually because of the naturality, because of this definition. This good, we define it so natural here, and we have good where I defined it here. We define the convolution like this, and we know that this M have good properties. One of them, the naturality. So this is why really we got here a simplicial distribution. For every x in x. So yeah, this is a multiplication, and it's the fact that this will be in this case this simplicial distribution x delta z m is simplicial is sorry, a convex monoid with this multiplication, what we define. Okay, let's give one example. Let me give you this example when x is the following. This is x. So what we mean by this when we write this is x, so x is a simplicial, we mean like this is what generating this, like how it's, or the realization of this as a topological. So we mean that in x0 we have, let's call it u and v. So we have u and v, this only two vertices. In x1 we have, like, let's call it sigma 1 and this sigma 2. So we have sigma 1 and sigma 2, but of course we have the degeneracy of this, like S0U and S0V. But this actually, it's like, in fact, this is like, this is, we imagine, like every vertex, we can imagine it as a line also, as a edge, okay, every vertex. And here in X2, we don't have any generating one, but we still have degeneracy, like we have S0 of sigma 1. So what is this 0 of sigma? What is it representing? Because every edge, we can think about this in two ways as a triangle. we can think about this one simplex as two simplex, one way by adding here one edge, like from U to U, this one. And then this will be the same V, this one way. So this is called S0 of this sigma. Yeah, this is only imagination, but this is good for the theory. Okay, we will, yeah, this is very good for the theory of simplicial sets, but and here we can add for this, for example, this one from V to V, and then we have here this UV. So this is S1 of sigma 1. Yeah. So we can do this, like, so we have this. Okay, we have, of course, here the degeneracy one of this. We have all the degeneracy and the other degeneracy for this also. Like we have also S0, S0 of U, or S1, S0 of V, or something like this. Yeah, we have many, but it's not important for us because all of them we can know by this. So the important things here when we define simplicial distribution on this, because what is simplicial distribution on this? It's a map from this to the distributions here on Z2 cross Z2. So everything generating by where we send sigma 1 and sigma 2. Like let's say like we send sigma 1 to this distribution on here, we can write like this. And let's say we send sigma 2 to distribution here, which we can write Q0, 0, Q1, Q1, 0, Q1, 1. By this, we can get everything because this is, in fact, we see in the picture, these are the generating of X, okay? This is the generating of X. So we can get U and V from them. So how we can get from this, the distribution on U and V? How we can get this and the distribution on U and V? So P of, because like we know that if we going D0 of sigma 1, we remember like this is how it's called, sigma 1 U V. So D0 of sigma 1, it's this U, right? No, this V. D0 of sigma 1 is this V. So if we going that, if we take the distribution, if we take sigma 1 and then we apply P, this will be the same as to applying first of all P on sigma 1, and then to take here this D0, but this will be D of D0. Okay. So we will get this from P of sigma 1. So what it's mean D of D0? It's mean D of D0 on this distribution P0, 0. So let me just tell you how we can act this D0 on this. So it means like we going and sum, because this will be distribution in here. This will be distribution on here, on Z2. So it's only two numbers. Like it's only, I need here one number that give me what about 0, what is the distribution on 0 and what's the distribution on 1. But what we take in here, like if I want D of D0 of this P, this is called, let's call it the big P, okay? On, for example, on 0. So you remember this is the sum of everything that give me 0 by applying D0, AB. But we know that it's by deleting, like by deleting the first one, it's give me 0. So by deleting the first one, it's give me 0. There is two options, we know, like this, 0, 0, and 1, 0, right? By deleting the first one, it's give me 0. So we should actually count this and this. So it will be B0, 0 plus B1, 0. Here, the same, B1, 1. Here will be, sorry, this the sum of this, both of this. Okay. So in fact, in this case, there is a good way to do this. Like we can think about in H like a matrix, like in H like a matrix, and in the end we will get by the sum of at here at the end, if we want D0, by the sum of the column, we will get this and we will get this. But if we want to get this from this one, we have to take the sum of the row. One can check it as I did here, the sum of the row. Okay. So but it have to be the same. This is exactly the non-cyclic. Okay, this is something that already Gian talked about. This is the non-cyclic. But the thing that if you take what I wanted to say, and maybe you should check it by yourself, because Ashrati, that really is a product, it's really going well. Yeah, like if we take now, so what we have, we said like distribution, it's only defined by have here distribution on this and distribution on this. Okay, let's say we have one distribution here. Like let me give you one distribution like this. Let's say quarter, half. Maybe I have here example. No, I don't have. Okay, quarter, half, quarter, 0. Let's say, and I have here some distribution. So I need here to be like this. The sum here to be like the sum here. So maybe I can take here half. 0, let's say quarter here, and then the sum of also I want here this to be, so the sum of this have to be there. This is good distribution because of the sum of this is equal to the sum of this, because here the end I can take by the sum of this to be the first of this, which is the sum of the lines. So this is a good distribution. One can check that it's really there is a non-singleting for here and here. Like here, the distribution will be in from this, we can get the distribution on this. Okay, let's say that we have another distribution like this, like let's say this distribution. This is also another distribution. Now, if we take the product of this will be a new distribution that here we have the convolution of two of this. And here's the convolution of two of this. And you can check that if we take the convolution, this will be really simplicial distribution. Like it's really have the non-singling here. It's have that if we marginal to here, it will be the same in both or here. So this is the definition. So that's why it took me time to define on the group itself, because everything's happen inside the group, inside like the convolution, by convolution. Okay, so this is how it looks like. Yeah, if we already say this, I want to say something about the degeneracy. I want to say something about the degeneracy. Maybe one can ask what happened if I have, we said what happened if we take the face, but what happened if we take the degeneracy of some distribution? Like if I have some distribution here, like let's say distribution in Z2, one have distribution in Z2, so we can write it's like, let's say 3/4, right? Like here, what is the 0 and the 1? So what happened if we take S0 of this? So even as a distribution, it will be as a distribution, so will be the same as this. Like it's like we said as image, like one edge, I can imagine it as a triangle, but it's really only edge because the same information, right? We say this about the degeneracy. What's the meaning of the degeneracy? So here it will be the same if we apply on distribution, because what it will have, it's saying that we can take like what it's, for example, on 0, 0. So we take all the thing that send me to 0, 0 here. So which one send me to 0, 0? I know if I copy 0. So it will be this 3/4. Okay. And if we want like for S0 for on 0, 1. So, but no copy give me to 0, 1. No copy of, because this is S0 what it's doing, S0 of A, it's AA. So I can get 0, 1, so that's why it's 0. So actually, in fact, you will get that D S0 of P, it will be 3 quarter here, and 0, 0. Okay? So it's the same information that we have here, but only like we only make it like look like bigger distribution, but with many zeros. None. Okay? So this will be good for the next talk, this degeneracy. Okay, let me now move to just a minute, sorry. Yeah. Okay. Sorry, I'm confusing. I wanted to stay in this example. I wanted to say something about this example. Like this example, what we did, all the simplicial distribution on this, delta Z2, it's a small example, so we can write the shape of all the simplicial distribution, because all the simplicial distribution is a convex set. You know what is a convex set? Convex set is something like this is not convex, you know, right? Like we can't here do convex combination, but we know that we can do convex combination here. But it's in fact even polytope, like that have finite number of vertices, something like this polytope. But of course it's much bigger dimension. So here for this, actually we can write the, like every point I mean here will be simplicial distribution. So what is the shape of this? So actually the shape of this in this case will be this. Something like this. It's not exactly, but something like this. Okay. Yeah. Where these ones are the deterministic, this one are the deterministic distribution by zeros and one. Like we have many, like I can write one maybe deterministic. This, for example, 0, 1, 0, 0. And here, how I need here to be 0, so maybe 0, 0, 1, and here it's 1. This will be, yeah, exactly. This is deterministic, for example, distribution. Example of them. There is 4 like this. It's not only any 0, 1, because it's have to match together. It has to match together. So this is the deterministic, and we have another 2 vertices here. These ones will be this one here. One of them is this one. And the other one, it's we replacing by this. This is the average, by the way. This is exactly S when we have right. This is S when we have, and this is I, right? When what I did before, the average group, and this form a group. This two, and this also the green one form a group. So it will be good exercise to see how this group acts. We say that this group, the deterministic, also here in the simplicial case, it acts on all the distribution here, in all the distribution. So it will be good to see how it's act on things, how it's act on this, how it's act, what it's make for the shape of this, because it will be a good point, a good start to understand this one, in order to understand some general facts that happen for something larger that we can see. But yeah, like this, we can write as this. This not exactly this. Like maybe this is a dimension here of the, because here in the inside the non-conceptual distribution inside there is. So the dimension of this is bigger, but it's, yeah, one can something like this. something like this. So it will be good as exercise again as to see how the green ones, this group, the Klein group act on the rest, especially on the vertices, what it's doing for the vertices. Of course, it's always this is a group. By the way, this is S. Something important to know that if we, in general, sorry, in general, if X is one-dimensional, what I mean one-dimensional, I mean that is generated by edges, something like this, for example. By edges only. Okay. Something like this. Let's say the simplicial, if it's one-dimensional, so always we can we have the group that sorry, the group of simplicial distributions on X delta Zm, simplicial distribution P, such that P for every edge, for every generating edge, sigma, P of sigma, it's exactly in here, in this group. Okay? Like we have many, like we can count how we have like this, of course, like how many generating edge, like let's say this is our group. So one distribution like this, for example, here I put S, here is 3, like let's say M is 10, and here is 9, and here is 7, and here I, and here S, and here. Why we can do this? Because actually, in fact, they are D0 of S or Di of S will be the uniform always. I didn't say this before. That is the fact that we can glue them to always of Sj, sorry, of any S, of any power. It will be the uniform always. So because of this fact, we always have this group in one dimensional, and one of the things that you can maybe start to think about it, it's how to generalize this for higher dimensional, this group. Because we saw, and we will show later, that this group is important for us, and we will show this maybe later. But it's you will see like later how vertices appear in this group, but it's good also to generalize, to think how to generalize this for higher dimensional, like when we have also edges and other things like triangles and things like this together. Yeah. As for now, it's like this. The last thing that I want to talk about is like we can only I need only, let's say, 10 minutes. Sorry. Okay. So we can talk about like I want to say that Y can be the outcome space can be any simplicial group, we say, right? And we take this is delta Z, but we can take any simplicial group, then even simplicial monoid, by the way, but it's okay, simplicial group, let's say, then the simplicial distribution of this is the convex monoid. So another important example when y is the nerve of Zm. This is important example. When y is the nerve, what is the nerve? It's have some topological meaning. It's have some important also for. But let's only explain this. Maybe later in other talks we will need this let's say homotopical meaning of this. But for now, let's say that how it's defined. So it's defined like this: like in the 0 degree, there is only one point, like the sets that have one point. Let's say 0, 0, 0, 1 point. This is a group that is with 0, only 0, and in the Z2. And here Z2 cross Z2 in the sky and like this. But like simplicial, let's say what is the degeneracy and faces maps. So here, of course, like we have only one option to send to this 0. Okay. But this one sent to 0, 0 only. This 0 by is 0. There is only one degeneracy map here. The faces maps here. So
you mean 0, I guess, right? It's not a 10.
Sorry, sorry. Yeah, sorry. And here for here there is 3. Like from here to here there is 3 faces maps, and the face map will be like this, like A, B. The first one, okay, D0, it's by omitting the first one. D2 by omitting the second one. A. But there is D1, this is important, this is the sum of them. We use the sum here we use the group structure of inside the Z2, because before we can do delta Z2, this we can do for every set. Okay, 8 we can do. But here really we use the structure in order to do this. The same here, one can imagine what happened here. Like here, we have D0, we omitting the first one. Then we sum this. Then we sum this. Then we omitting the last one. So like this, it's going like this. And for the degeneracy maps, we adding 0. It's not by copying something or creating something, but it's by adding the 0. So for example, here we have S0 and S1, right? Here we have. So S0, something A going to 0A. We add 0 in the 0 place. And here, this is S0, and S1 will be A0. And the same, for the rest is the same. Okay, one can really prove that really it's a simplicial set. It's non-simplicial set. There is also this come from the nerve of category anyway, but you see that it's related somehow to, it looks like it's related somehow to the delta Z2. Also, we will not going to show it's here, like we not really need this. We need this later. It's somehow related. We will show how it's related. But when we use this, the thing that in order to explain the same thing, same thing, we need now one dimension higher dimension. Why? Because like let's back to, for example, to delta Z. If I want to explain the CH/SH scenario, you remember this one that we have for okay, I will not back to what it's by observer and things what Gian explained, but let's explain this when we have delta Z2. So this is the outcome space and this is the measurement space. So in fact, we have like distribution on here. What is distribution on here? Distribution on here, there is some distribution from here, like on generating, but generating will send me here to the first degree, but it will be here. So we have 4 P's, let's say this sigma 1, sigma 2, sigma 3, sigma 4, P, sigma 1, sigma 2, sigma 3, sigma 4 in here, okay? In here as that much together somehow. But when we want to describe this, when we have a nerve, it's not the same, because if we take, like, if we have a nerve now, Z2, and we take this, it's not good, because it's only give me like something on here. It's give me one dimensional, so it give me where is one dimensional here, and Z is a nerve in one dimensional, we have Z2. But I need a distribution on Z2 cross Z2, okay? But we can do this, it's not important, but we need here triangles that are triangles that glued together, not edges, when we take the nerve. So it's actually, it seems like, okay, it's one can think it's harder now, but it's give us more opportunity to glue the triangle, because there is like one way. Forget about directions. There is one way to do for the edges. If we ignore the directions, but for triangle we can choose, for example, this to be like we have this. Okay, this like one edges, and there is one in one like as we have before, like one, and as this is connected with other to say that there is one, like here the same, they have the same measurement here, so the measurement will be this one, okay, and this connected, this triangle connected with this, and this triangle connected with this, and this triangle connected with this, okay, it's like this. And this will be good because okay, we should choose direction. Usually we take the cone, maybe Salman can talk about this. We took the cone of what we had before. Anyway, and we can choose like something else, for example, we can choose this, the torus one. Like when we have something like this, when this edge is glued with this edge, and this edge was glue with this edge, and really it's good actually, this one, because in this what Jihan, I remember, suggested the first one, so he has this idea to, when we how to topologically describe conceptuality, like when we can feel it, something like this maybe also Salman can talk about this next to talk or something. But really, so we have some uses, because we have some application if we choose different choices of triangles. And the other benefit that we can get from this nerve, the other benefit that we write the distribution inside this, like as I wrote as a matrix, but now we can write the distribution here in this way, like P0, okay, maybe let's write bigger triangle. Like before, when I have edges, so I wrote it like this, right? Matrix, and I told you that we should, like, if we have this direction, so this tell me that I need here this the sum to be the same as the sum of this and things like this. Now, we don't have to remember this for triangle. If we put it as a triangle, let's say this triangle, so we can put here P00, and inside this in P11, and here P, I don't remember, one of them 01, one of them 10. We can check, but I think I wrote it here somewhere. You remember, Jihan? Which one 01, which one 10? Let me write this. Where I have this? I think I have this somewhere here.
01 on the left.
I have, yeah. Where?
0.
0. Inside, we can change, because this is 01, so this when we deleting the, so this 10, right? This is 01.
Yeah.
Yeah. So exactly, and when we glue with another one, when we glue with let's say with this, and here with another one like this. And by the same way, we write here also Q 0, 0, and here where is Q11, let's say, and here also what we say like 0, so there is Q10, Q 01. You see inside the edge, we put this in the middle, and we say inside edges like this in some direction, and then we need to check that the sum of this equal to the sum of this. You can find it in the paper simplicial conceptuality, the first paper, okay? Simplicial quantum contextuality. So we need also to check that this can remind us, and the same here. Like for example, we will have here another one, so we need to check that the sum here equal to sum here. This is how we can glue triangles. So sometimes in using triangles can be really helpful, and in fact maybe we'll show this later that the theory of this included in here. This is included in here, of course, not the same one, but yeah. Yeah, here we have more. Like the torus, for example, what I explained before, we can't do this in here. Okay, anyway, it's two different approaches, and we still have this the direction that we need to fix. Like we need somehow to. I don't have the camera. Why? Yeah. I close it when I had the alarm and then yeah. So we can yeah, we can talk about this. This is still issue to deal with. What about direction? Which is the best direction? Things like this, yeah. Okay, so I think I finished. I thought maybe I can talk about a little bit about action on Bell inequalities, maybe in future talk or something.
Okay, I think it sounds good. Thank you very much, Aziz. Yeah. So any questions? So yeah, I think yeah. So as you noted, I guess action on the Bell inequalities. Maybe Salman is going to talk about it. But it's great that you mentioned the NURBS at mod 2 construction because it may be needed next time. So next time will be about more on the polytope structure of distributions. Yeah. But then I think we have to decide the talk after that once we get there. But anyways, I think this was very nice. This product structure is something new for these distributions, and they have this interesting structure, the interplay between the monoids and convexity. So I really find this product of these simplicial distributions quite amazing. There's a very interesting structure there to be studied further, right?
Yeah. I think we still don't know.
Yeah. I think even these simple examples. I think the example you showed with this one-dimensional space where you labeled the edges with SJs. So that looks quite interesting. So are they always vertices if you have these kind of SJ distributions on the edges of that one-dimensional thing?
So you mean this example? I think with the average. Yeah. This appear actually everywhere, like because
this is something like a PR box kind of thing, right?
Yeah, here.
So that one, yeah.
Yeah, exactly. You can find something like this, any of this to choose, and you have many like this, yeah, right? Because you can count out like if you have edges, like let's say 7 edges, and you have G here, you can find any like M is 10, so you can find 10, 70 like this, right?
Yeah.
For every edge, you can choose whatever.
Okay.
It's 7 and 10. Sorry, 7 and 10. Yeah, like it's more. So what is 70? Sorry, 7 power, right? It's 10 power 7. Like if you are in Z10, for example.
How many edges are you taking?
Like if you have this, for example, this one, the K33. How many edges here? We have 9, right? Or 6?
Yeah.
How many edges we have? No,
9 edges.
9 edges. Okay. So we have 9 edges. And let's say we work on that 3.
Yeah.
So this group will be 3 power 9, right? Because 3 everywhere you can put one of the 3, right?
Yeah.
3 power 9, yeah, which is a huge number. Yeah, and
Yeah, it's a large number.
it's and if you take the convex of this is also convex monoid inside this, yeah.
So are you going to come back to this in the homotopical vertex classification?
Yes,
yeah.
Yes.
I think that's the proof, right? That's one way to prove that.
By the way, if you have time, I want to suggest you about the Bell inequality, how we can define Bell inequality.
Yeah. Oh, okay. Yeah. So that would be perfect. So let me stop the recording then. Okay.
Yeah.
For the rest.
Yeah, Salman 0. So I want to